Thank you so much for inviting me here. I'm going to explain you a bit about 5G technology and answer the question if it will be really as disruptive as people as expect, or is more like more the same as 4G. It seems that technology is not helping us at the moment, and also try to focus a bit on what spectrum we need for 5G. Voila. Okay. It's this one, no? Okay, voila. Seems that I had a different size of the slide, but it's not a big problem. I can keep speaking. So anyway, what I wanted to start with, we all know why we want 5G. We want more and more data, and a lot of people have predicted more and more data requirements over the past years. There's lots of numbers and predictions, but one moderate prediction is 38% every year, which means a factor 2 every 2 years. So how do we typically achieve this? We need more bits per second per area, which is more spectrum, more cells, and also more bits per frequency. That's what we need to do. That's what technology has to deliver. But how disruptive is that? If we go back to history, then we see Cooper's law. I don't know how familiar with Cooper's law, but Cooper's law has shown us that already for 100 years, wireless capacity has doubled, not every 2 years, but every 2.5 years. So if we just follow that trend, 5G is more or less just the same. And if you want to look on how this was achieved in the past, then we see, I actually have a nice plot, and I don't even know if I remember it by heart. Oh, thank you so much. Cooper's law has given us spectrum utilization has doubled every 2.5 years. Over the last 100 years, it has been happening over and over again. It has given us more than a factor million over the last 60 years. And if you look how this has happened, how does it happen? A factor 5 was given by a better link capacity, which means if you have a given frequency, you're able to deliver more and more bits in that same band. This is by using better modulation and coding techniques, massive MIMO or MIMO, etc. Another 25% has been giving more spectrum. We always open up more frequency bands, and we continue doing so for 5G. The biggest gain, however, has been achieved by densifying the spectrum. More and more cells, a factor 1600. And a factor 5 has been given by better hardware, which means we can put the bands closer together. In the past, we have increased the capacity by densifying the network, and this is also something people expect to continue for 5G. But then, 2 years ago, the death of 5G was announced. It was an article in the US by some colleagues from the UT Austin. They said that densification will be the death of 5G. Why? There's too much interference if you keep adding small cells. And if you have very small cells, it becomes a nightmare to do handover, to deal with mobility. Luckily, in Europe, we announced a technology that could save 5G. We responded with an article and called it the resurrection of 5G. And what was the European answer to the resurrection of 5G? It was massive MIMO. I don't know if you're very familiar with the difference between massive MIMO and millimeter wave. Massive MIMO is a technology, I'll try to explain it to you now, that is pushed a lot by European vendors and also by European research groups. We strongly believe in it as an answer to 5G and the frequency bands below 6 GHz. It's a prime candidate to improve spectral efficiency at 700 MHz or maybe even 3.4 GHz. Technology is there. Researchers of Lund University and Bristol in the UK have demonstrated a row 176 bits per second per hertz using massive MIMO technology. If you compare to 4G, IMT advanced spec, 3 bits per second per hertz. This is a huge improvement, a lot more than the 30% we need. How was it achieved? What is Massive MIMO? It uses a lot of antennas at the base station, and by doing some clever signal processing, we can serve many users at the same time. In the previous demonstration, they actually served 20 users in the same time and frequency slot. By doing so, you can increase spectral efficiency with a factor 20. The big advantage is you don't need more cells. You just need to add more antennas at the base station. And you can keep using the same spectrum and just increase spectral resolution there. Okay. I made a slide once a long time ago when I was thinking about 5G, what I thought was 5G and what technology we would need to develop for 5G. First flavor of 5G I thought was the coverage and capacity flavor, which is the domain where the traditional operators are, of course, the champions. In this flavor of 5G, we need anytime, anywhere guaranteed service. We need expensive sites, big base stations, and exclusive frequency bands. Prime frequency bands below 6 gigahertz. This flavor of 5G is a flavor where Massive MIMO is a good solution to keep improving spectral efficiency in addition to maybe more frequency band. And Europe is good in Massive MIMO. Another flavor of 5G where we want to go is maybe indoor capacity. We're talking about telesurgery. We're talking about virtual reality as new applications. But even applications of today, being here in a conference room in your home office, most of these applications are indoor. So we need a lot more good coverage indoor. And we all know that these base stations are not a very clever method to service indoor users. It's like using the outdoor light streets for illuminating your room. Every room has also lights indoor. We need indoor base stations to have better indoor capacity. So for indoor capacity, it's maybe not the operators who are the champions, but maybe the building owners, because they own the facility. There we'll have ultra-dense deployments. This building owner just puts base stations or small base stations, you cannot really call it base stations, Wi-Fi access points or the next generation Wi-Fi access points. And there's no site costs. There's maybe unlicensed spectrum, Wi-Fi bands, but we pay for the backhaul, the service to the home. And we've heard already a new term this morning, fiber to 5G. This is really here where the business is. A third flavor of 5G, I believe, is a massive and critical. Machine-to-machine, ultra-low latency. There, I believe, we need thin operators. And you have seen a lot of them coming already. LoRa Sigfox, they're extremely light and thin networks. They have only one killer app, but they're very thin and lightweight, and as such, they can build a business model quickly, a lot faster than the operators, actually. For those, you need few sites, prime unlicensed spectrum. That's what LoRa and Sigfox use. Anyway, if you look in this partitioning of 5G, then you see here you need the prime frequency bands, which are very important. 700 megahertz, maybe 3.4 will also do the bill. And the technology there that I believe in is Massive MIMO. Here, we maybe need unlicensed bands, but we need a lot of bandwidth. So where can we find a lot of bandwidth? It was already mentioned here, millimeter be an excellent candidate to give you very high throughput indoor. But then we need to get to the home. And therefore, a millimeter wave point-to-point backhaul link, I learned a new term this today, fiber to 5G, is probably a very good candidate. And millimeter wave might be a good candidate there. Massive MIMO might also be, but maybe if we have very directional point-to-point links high up, then millimeter wave could maybe be an answer if weather conditions are not too negative, because we have to be aware that if you have a lot of fog or rain, it might already block millimeter wave. But it could be, if you have very directional links and you have very good antennas, it might work for relatively short distances. And the advantage is, in these cases, you have small cells and very directional links, but you have no mobility, you can plan it very well, so it can be done. So another thing I want to say here, we can do trials for millimeter wave. Technology is there. In the US, there have been a lot of trials already in 28. I think it's also now important to start doing trials. Technology, mass production of technology, millimeter wave technology, might take a little while because it's very difficult to build the technology. So you can build the technology and calibrate it well, and you can build it for a trial, but it's not yet there for mass production. But why should we wait for mass production? We can already do some trials and see if the links, the few links we can build and the few chips that are there and well calibrated, we can already use them and see if they can give a good enough service in all weather conditions. So then the last thing I want to say about 5G is, should we design for the killer app or for ultimate flexibility? We've seen already many presentations, also today, where people want to have low latency, high throughput. They want to have everything together in one technology, which is, of course, very difficult. If you think about the 2G technology, it was application-specific design for voice communication, and it worked very good for that application. It was very cheap and reliable. And in 5G, people want everything. Very high data rates, very high capacity, reliability, low latency, long battery lifetime, and it should be cheap because people want to pay less and less. The billion-dollar question, what is the good trade-off between performance and flexibility for 5G? That's really something we have not answered today. And one question is, will 5G be a design nightmare? I don't know if it's a coincidence, but there are no vendors here. Maybe they are working very hard on this design nightmare. Because it's not easy to know what's the best strategy. And this is something I want to show just to explain to you that there's always a trade-off between latency and flexibility. So no way we will have the 1 millisecond latency with all flexibility you want. It's impossible. And I'm not going to explain all the terms that are on this slide, but we have to be aware that the rainbow of requirements of 5G cannot be served with one single technology. Voilà the conclusions. I believe there are clear favors in 5G. One is the coverage, prime spectrum, massive MIMO. The other one is indoor capacity. Millimeter wave is the technology to look at. Each use case, I think, needs a different technology and different type of frequency bands. Massive MIMO, there Europe has a lot of experience, and we did a lot of tries already. In the US, there have been a lot of millimeter wave tries already. The technology is there, not for mass deployment, but for trials, and it's really important, I think, to do more of them, also in Europe. And a key challenge or answer that still needs to be answered, it's also not yet clear for me, what's the level of trade-off between performance and flexibility in 5G? Voilà, I'm sorry for the technical challenges. I hope the message was still clear. Thank you.